Hello, my name is Nikolas Ringas, and I'm here to present the experimental research conducted at the University of Edinburgh School of Engineering on the fastener behavior in light-gauge steel stud walls under cyclic and monotonic actions. Current construction trends aim towards tailor-made prefabricated solutions that lead to less labor-intensive on-site activities, construction time minimization, and harnessing the materials' full potential. This is driving the industry towards a more sustainable and efficient construction framework using materials that can be fully recycled. So this is where light-gauge steel frames come to the picture. Light-gauge steel frames are efficient and modular structures with an ability to resist lateral loading conditions. However, such applications involve the installation of bracing, which require a high level of manufacturing detail and thus increase erection time. Such wall assemblies also employ sheathing boards, which are commonly regarded as non-structural components and are used for insulation, same as in ordinary built walls. Nevertheless, research has shown that they influence the framing system, resulting in composite action, making them act as diaphragms against lateral loads, increasing the frame's axial capacity and serving as a potential substitute to X or K bracing. Yet, their effects are currently neglected by modern structural design codes, while their structural behavior has not been thoroughly investigated. So through our research, we set the aims to investigate the shear resistance of a sheathed framing system under cyclic and monotonic excitations, and to understand the influence of the fastener behavior on the composite system. These were followed by the testing of the mechanical properties of the employed materials, meaning the calcium silicate boards and light gauge steel. As explained, for the purposes of our research, we conducted material testing of the employed materials under tension and compression. Those were followed by our investigation to determine the connection behavior for the composite system for a direct pull, screw pull-out, and push-out testing under monotonic and cyclic actions. The first step was to test the light gauge steel, following the guidelines on ISO 6892-1. Through them, we recorded an average Young's modulus of almost 193 gigapascals, a yield stress of 447 megapascals, and an ultimate stress of 595.6 megapascals. Then, we continued with the material testing of the calcium silicate sheathing board. As there was an absence of a specifically developed European standard for calcium silicate testing, we used the American standards for both the tensile coupon testing and the compressive coupons, with the standards listed on this part of our slide. Through these tests, we recorded a mean value of 3.8 gigapascals for the Young's modulus and 30 megapascals for the ultimate stress of the compressive coupon parallel to the surface, while their failure mode was a sudden shear crack and loss of bearing capacity, as shown by the peak on the top left graph. Meanwhile, for the compression normal to the specimen and surface tests, we obtained a value of 1.3 gigapascals for the Young's modulus and 61.4 megapascals for the ultimate stress. That value was measured as the stress at 5% deformation as specified on ASTM C165-07. Finally, for the tensile coupon testing of the calcium silicate board, we recorded the value of 10 gigapascals for the Young's modulus and an ultimate failure stress of 6.1 megapascals. Then we continued with the direct screw pullout testing. For the measurement of the direct screw pullout, an in-house testing setup was made comprising of a steel stud and a piece of CSP screwed onto the stud through a single fastener. The screw was then pulled through an inverted T-section that was gripped by our actuator. For reference, we also recorded the capacity of the connection for a bare screw and Lightgauge steel connection. Through our tests, we observed two failure modes. The first one was a result of the gradual loss of thread engagement due to localized damage of the thread, as shown on the sketch. In simple terms, failure mode 1 is a localized shear failure of the screw thread. Evidently, the capacity of the connection experiences a sudden drop due to the initial breaking of the thread, and then it picks up until it reaches its maximum capacity of about 4 kilonewtons and before breaking completely. Then, for the second failure mode, there was no damage on the screw, rather than a failure of the hole on the steel stud. As shown on the above force displacement graph, the ultimate capacity for the composite connection was again close to 4 kilonewtons, as in failure mode 1. As explained earlier, for reference we recorded the capacity of a bare steel connection as well. That one failed after almost 2 kilonewtons, which, although was less than the composite connection, it was more than 60% stronger than what was predicted from Eurocode 3. For our last set of experiments, we've tested the shear behavior of the fastener through push-up testing. The setup comprised of a double-lipped steel stud, 12 mm calcium silicate boards on each side, and self-tapping screws with a 300 mm spacing in between. For the monotonic experiments, we followed a loading and loading sequence as prescribed on BSEN 383 and measured a maximum load of 3.7 kilonewtons per screw, 2.5 kilonewtons yield load, and an ultimate slip of 7.6 millimeters. Moreover, the initial stiffness per connector was almost 1000 newtons per millimeter. Evidently, the system presented good ductility between the Lightgauge steel and calcium silicate boards, with a sufficient redistribution of longitudinal forces. The only failures observed on the specimens were a tilting behavior of the screw and subsequently a bearing failure of the screw hole on the seating board. For the cyclic experiments, we used the Curie loading protocol for ordinary ground motions. Through our 4 tests, we observed a significant pinching behavior in both loading directions, with gradual hole enlargement in the bearing interface between the calcium silicate and the Lightgauge steel. Also, as shown on the envelope curves, good convergence was achieved for all of our experiments under cyclic excitations. In conclusion, a series of tests were conducted to investigate the composite action on panels made of Lightgauge steel and calcium silicate boards connecting with self-tapping screws. Through our investigation, we observed that the seating component we used significantly improves the direct screw pull-out capacity, exceeding the predictions on Eurocode 3. The framing component's shear behavior was also investigated for cyclic and monotonic actions. Through them, we observed the screw tilting behavior and the bearing failure of the calcium silicate board. All the experiments, both under cyclic and monotonic actions, are in good agreement. Of course, our research will be further expanded in order to understand the influence of the fastener behavior on the composite system. Current research at the University of Cambridge will evaluate the experimental framework numerically with the overall aim of increasing the accuracy in structural design and produce a framework that accounts for composite action. Finally, we would like to thank Construction Scotland Innovation Centre for funding our research through the ICON Challenge Fund, and Newton Steel Framing for providing the necessary materials to finish our research. Thank you for your attention.